Okay, everyone, let's get started. So welcome back. We'll be in the lab this week, so make sure you report to lab on Wednesday or Thursday, depending on what section you're registered for. And you're going to want to pick your lab partners as soon as possible. So when you find a partner to work with, just send me an email. It's okay if you wait till your lab day. Just let me know who one of the two partners should send me an email so I can record that. If you want to work alone, you're welcome to, but just keep in mind that the expectations will be the same whether you're in a two-person group or a one-person group. Okay? Okay, so last time, it's been a little while since we met, but last time we talked about programmed I/O, which is the way that CPUs initiate communication with peripherals or external devices. We also talked about bit twiddling, which is reading and writing individual bit fields within control and status registers, which are the actual values that the CPU is conveying back and forth to the peripherals with programmed I/O. And we talked about pulse width modulation, which is the way a CPU can control an analog device using a digital signal. And then we started talking about interrupts, which is the way that a peripheral can request that the CPU execute some code on its behalf, basically getting the CPU's attention. We didn't finish that yet, so I'm going to finish up that material today. I've got quiz 1 is posted on Blackboard. I think there's 7 questions on there, multiple choice. You can take it twice, and you have a week to take it. I'm going to try to have 1 quiz per week from here on in, so if you go on Blackboard, there's a link to the quiz right on the schedule for that week. And like I said, you have just make sure you take it sometime this week. It basically reviews the material from the previous lecture. In this case, it's the material from 2 weeks ago. Okay? Right, so about the interrupts. So we talked about 2 ways to do interrupts, level triggered and edge triggered. So basically the idea is that the peripheral has a wire that goes back to the CPU, a single bit wire. And it gets the CPU's attention by changing the value on that wire. If it does it with by level, so the CPU could respond to the level being high on that wire, or it could be an edge triggered where the CPU is looking for a transition from low to high or from high to low, right? The problem with this is that it's a way that the peripheral gets the CPU's attention, and when it does get the CPU's attention, the CPU will go into an interrupt service routine. So it'll start executing some code that will, usually the code checks to see what the CPU needs to do, what sort of event it has to respond to. The problem is that if there's no way for the CPU to communicate back to the peripheral, I mean, of course, it could use programmed I/O to do that, but just in the case of the interrupt mechanism, this is just a one-way street. The peripheral raises an interrupt, the CPU responds to it. The problem is that, for instance, if you have a level triggered interrupt, the peripheral may keep the level in an interrupt state, or in this case a high state, for too long. And it may falsely cause the CPU to think there was 2 interrupts when in fact there were just 1. Likewise, with an edge triggered, you may have the reverse problem where the device tries to get the CPU's attention a second time before the CPU is finished responding to the first interrupt. Right, so that's a problem. And so the way to solve that is to have another wire that goes back from the CPU to the peripheral, which would be an acknowledge wire. So that way, you can have a handshake between the device and the CPU for processing the interrupt. So the device could raise the interrupt wire, and the CPU could then go into the interrupt service routine. But when it gets in there, and sometimes it takes some time to get in there. Sometimes the CPU is doing something that can't be interrupted right away. But the CPU will start responding to that interrupt, and when it does, it'll raise an acknowledgement flag, which tells the peripheral that the CPU has acknowledged the interrupt, which allows the peripheral to drop its interrupt request. And when that happens, the CPU can likewise drop its acknowledge. So that way the CPU the peripheral knows how long to hold the interrupt high. And also the CPU knows that it's not going to respond to a second interrupt until the peripheral drops the interrupt request, right? At which point it drops the acknowledgement, right? So basically you get one interrupt service routine per acknowledgement, right? Make sense? So it's just a handshaking protocol. Yes?
So just making sure the acknowledge is sent when the CPU begins its interrupt service routine.
Yeah, the acknowledge, yeah. So sometimes there may be a delay there between when the interrupt request from the peripheral goes high and when the CPU acknowledges. That's right. And likewise, the peripheral may take some time between when it gets the acknowledgement and when it drops the interrupt request, right? The point, though, is that you go through this handshake to synchronize the two, right? So it's just another style. And you might say, well, which CPUs have which type? Well, it depends. The Arduino CPUs just have the one interrupt request. There's no acknowledgement. If you go to an embedded, like a heavier weight embedded CPU, like an ARM CPU, like the one that's in your phones, it has a more sophisticated interrupt system that has an acknowledgement, right? So that's the difference. Okay, so that was the only other thing I wanted to say about interrupts. So today I'm going to start talking about interface protocols. So I'm going to review the types, and then I'm going to talk about one in particular, SPI, because that's going to be what you need to do the lab assignment for this week and next week. The lab is posted on Dropbox, and we have a lengthy description of the lab on there, as well as a skeleton that you can download, and you can put your code in that skeleton. Now I'll talk about the lab in more detail in the lab session. I'll go over the lab sheet. But for today, I'm just going to give you a quick summary so you have an idea of what it involves. So basically, the idea is that you're going to build a software-based SPI decoder. So you're going to read a signal trace file, which is a text file that shows signals versus time, and then you're going to decode the transactions that occurred in those signal traces, right? And so this is just software for now. In the next project, the next lab, we're going to have you implement this in hardware on an FPGA, but for now, just to understand how the protocol works, you're just going to do a software-based decoder, right? So when I talk about interface protocols, I mean any type of communication that's done between chips or between circuit boards or between modules, right? So what I'm talking about is, for example, or even inside a chip, like on a system on chip. So they have on-chip buses, like the ones that we're going to use on the FPGA, called AXI, for instance, which is the ARM standard, and it's a bus that's used for connecting components on chip, and it's a parallel bus. It's usually anywhere from 32 bits wide to 512 bits wide. And it's a high-performance bus that's used to connect components on a chip. Then if you go a chip-to-chip type of connection would be something like PCI Express. I'm sure most of you have heard of that. That's how, like your graphics cards and your network cards connect to your CPU. And other ones are QPI, Rapid I/O, and then there's SPI and I2C, which are the two that we're going to cover in this class in more detail. They're the simpler types. And then, like, for example, if it's a network, like a local area network, then you'll be using like Ethernet or InfiniBand or something like that. So there's these basically different types of interfaces. So there's some trade-offs here. Generally, the longer haul you go, the slower. So if you're talking about components communicating inside of a chip, it's going to be a very fast connection, very fast channel in terms of both the bandwidth and the latency. But if you go you stretch it out and you go through, to a local area network where you're sending signals longer distances, then it's going to be slower. But there's also a trade-off between high power and low power. So for example, if you're doing a chip-to-chip, PCI Express or like Thunderbolt, for instance, is going to be about the same scale as in terms of the distance that you're going to the SPI and I2C protocols that we're talking about in this class, but we're focusing on the I2C and SPI because they're lower power and lower performance, right? So in other words, what I'm saying is there's two trade-offs here. One is when you go longer distance, you're going to be slower, but also there's this trade-off between power and speed as well. So we're going to be focusing on these kind of lower performance, lower power protocols, and also they're simpler. They're a little easier to digest in class. And then we'll also talk about UART, which is specifically for console I/O, like keyboard and mouse type I/O. So there's two types of channels, asynchronous and synchronous. You might have covered this in 212. Asynchronous is when there's no clock signal that's part of the channel. So the channel, which is a group of wires that connect two things, doesn't have a clock. So you've got bits that are changing, you've got wires that are changing voltages, but there's no clock. So the protocol has to figure out a way to either extract the clock based on the signaling rate on the wires, or you can also, like UART, have a situation where the sender and the receiver side of the channel just agree beforehand on what the speed of the channel is, right? And so then they use their internal clocks, right? Now, if you do that, you're going to be more limited in speed as compared to having a channel where you kind of use an analog circuit to infer what the clock is based on the switching rate of the bits. That's how PCI works, for instance, PCI Express. You guys with me? Okay, so that's asynchronous, and synchronous is when you just have a clock signal in the channel. And that way, both sides use that clock to figure out how long each bit is in the channel for, right? So with a synchronous protocol, generally, I think this is always the case, there's going to be, whenever you have a clock in the channel, you have to have someone responsible for driving the clock, for putting the clock there and setting it. And generally that's going to be one side of the channel, so that there's basically different rules in the channel. So generally speaking, there's going to be like a master side that's going to be kind of like basically represents the CPU side essentially. And it's going to be driving the clock, it's going to be setting the clock signal, it's going to be determining what speed the channel runs at. Now if it tries to run the channel faster than the other side, the slave side can read, then that's a problem, then it's broken, right? So generally speaking with these protocols, there are either set speeds that it's expected to run at, or there's limits, right? But the idea is that you've got one side that's injecting the clock into the channel and is determining the speed at which the communication takes place. And so that's how SPI works, and SPI is synchronous. Also, with SPI, only the master side can initiate a communication, which is similar to what we talked about with programmed I/O. In programmed I/O, you had the CPU, and then you had peripherals, you had I/O, external devices, and a programmed I/O was fundamentally based on the CPU doing a load or store in order to read or write a value between itself and a peripheral, right? And the target of that transaction was determined by the address, the memory address, which isn't really a memory address because you're not addressing memory, you're addressing a device, right? SPI works the same way. So as you might imagine, SPI is designed for that same kind of an environment where you've got a CPU and you've got peripherals, and the CPU is coordinating everything, is orchestrating everything. So the CPU initiates transactions, and the peripherals have to respond. And so it's more of a one-sided conversation. Kind of, I mean, both sides talk, but only one side gets to decide when the communication takes place. Okay, so now the one thing that's weird about SPI, though, I found this to be very strange, is SPI requires that for every bit you send from one side to the other, you have to send a bit in the reverse direction. So every bit that's sent across an SPI channel, and it's a bidirectional technology, so bits go both directions, but for every bit sent in one direction, another bit has to come back. So everything is an exchange base. Every communication is an exchange the same amount of data going each way. Does that make sense? Now, why would it do that? Because sometimes you don't want to do an exchange, right? Depending on your application, you may not want to do an exchange. You may just want to send data one direction or the other, right? Why do we have to always send data both directions? That's just how SPI works. If there is no need to send data in one of the two directions, then just a 0 is sent generally. It's basically wasted, right? But there's still, according to the protocol, there's still this, bidirectional, every bit is sent both directions across the channel. So, so kind of to summarize here, with SPI, you can have one device that's in this master role that initiates the transactions, and that represents the CPU or whatever the, whatever the thing is that's running the software, that's running the system, and then you have slaves, one or more slaves, that have to respond, that they act like I/O devices or the peripherals. Usually there's just one, usually it's just a two-sided, but there is a way that you can set up multiple slaves on one SPI channel, and I'll talk about that a little bit later. But SPI isn't really designed for that, though, right? So generally speaking, you have just two sides. There's another protocol that we'll get into called I2C that's designed more for having, it's a multi-master bus where anyone can initiate, and you can have a bunch of things on one channel, right? A lot of devices hung to a channel, whereas SPI is really just designed for point-to-point. SPI is also byte-oriented, so all the transmissions are in multiples of 8 bits, which I'm sure isn't a surprise to you. But the bit ordering is application defined, and you might say, what do you mean by bit ordering? Well, SPI, I didn't put it on here, I should have, but it stands for it's up there, Serial Peripheral Interface, and it's serial, meaning that there's only one bit is sent at a time. It's not a parallel bus. So when you send each bit, you send them in groups of 8 bits, but the order of those bits depends on the application, and that's something that you have to know before you start using it. It's not encoded in the spec. It's something that, for example, if you want to talk to a new peripheral, you better check to see which bit ordering that peripheral uses before you start speaking SPI to it. Does that make sense? Okay. So SPI channel is comprised of 4 physical signals. There's the clock, as I mentioned, and the clock goes from the master to the slave, and then there's the master out, slave in, MOSI. That's the connection that goes from the master to the slave, and then as I mentioned, every bit that's sent is sent in both directions. It's always an exchange. So there's also a MISO, which is master in, slave out, which is the slave sending a bit back to the master. And then there's SS called slave select, which is the way that the master initiates a communication, right? You guys with me? So basically, there's 3 wires that they're all single directional wires. So there's 3 wires that go from the master to the slave directionally, right? That flows, bits flow from the master to slave along 3 of these wires, and only one of them is the opposite direction from the slave back to the master. Okay? Now, the clock, this is also kind of strange. I mean, it makes sense when you think about it, but normally when you think of a clock signal, like when you guys took 212 and you were talking about designing architectures and CPUs, generally when you design hardware, the clock is always going. Always. You always have a clock. The clock is kind of like the heartbeat of the circuit. If the clock flatlines, you're dead. Nothing works, right? But in a synchronous communication channel, you can actually just have the clock run whenever you're actually actively communicating. So whenever there's not a communication happening on a channel, the clock is idle, meaning it's just flatlined, right? Which, again, this is something unique to communication channels as opposed to digital logic designs, right? In a digital logic design, your clock, goes forever. As long as the chip is powered up, generally you're going to have a clock signal. And then, so basically the way it works is that when the master wants to do a transaction, it asserts the slave select, and the slave select is active low. So the slave select is normally high when the channel is idle, and then when the master wants to make a transaction, it drives the slave select low, to a 0 value, ground, low, low voltage. And then it keeps it low for as long as the communication is happening, and also during that time, it's driving the clock, right? And so basically for the entire time the slave select is asserted, you've got the clock going and you've got bits transacting, right, flowing, right? You got in both directions, right? That's basically how it works in a nutshell. So as I mentioned, you can hold the slave select down for kind of an arbitrary amount of time, but it should be, it's supposed to be, if you're following the SPI spec, it's supposed to be for a multiple of 8 clock cycles, right? So you can do it for 8 clock cycles or 16 or 24, you know, it's multiples of 8, right? Okay. So yeah, as I mentioned, the master drives the clock, typically is a few megahertz, and megahertz means megabits in terms of throughput. It selects the slave by setting the SS to low, as I mentioned, and then during each cycle, the master sends a bit to the slave on the MOSI, and the slave sends a bit back to the master on the MISO, right? So it's kind of like, it's almost kind of like a shift register. You could think of it that way, where the master sends one bit out into the slave, and since all the bits are flowing in the same order, you could think of it as like a giant ring, right? And in every cycle, the bits move one position on the ring, and after 8 cycles, you've performed an exchange, where all the original bits that were in the master are now in the slave, and vice versa. Make sense? Okay, so now one of the things that's a little confusing about SPI, and I don't know why it's like this, actually. I think I suspect that when the SPI spec was originally developed, by the way, it's supposed to be a standard, right? So the idea is that when you buy components, like for your Arduino, like when you build a system, you build hardware, you build you build some kind of a device. SPI is one of the standard protocols that are used to allow off-the-shelf components to communicate. But when they were originally developing SPI, I think there was some disagreements with the timing and how the exact timing was supposed to work. And so as a result, we have different modes for the channel. So before you use an SPI channel, you have to make sure that the master side and the slave side agree on what timing mode that they want to use for the channel. Otherwise, there'll be a synchronization error. Okay. Specifically, there's 2 parameters. One's called CPOL and CFA. CPOL is the clock polarity, stands for clock polarity, and it defines what value the clock is at when it's not clocking, right? When it's idle. So I mentioned that the master only drives the clock when communication is happening, when the channel is active. But when it's not, when it's idle, is the clock 0 or 1? Is it logic low or logic high? And the CPOL is the parameter that determines that. So if CPOL is 0, it means the clock idles at 0. And if the CPOL is 1, the clock idles at 1. Now I already told you guys that the slave select idles at 1 all the time, no matter what. That's not an option. So the slave select is always active low, and I don't know why it's active low, but that's the spec. But the clock can be idling at 1 or at 0. Now you might say, well, why is that important? Well, because that will determine what the first edge of the clock is when the channel becomes active. If it's going to be a falling edge or a rising edge, right? And the receiver it needs to know, what edge it needs to be clocking data on. Okay. Now there's another parameter called CFA, and this one is a little bit harder to get your head around. This stands for clock phase. So basically, what it's telling, or what it defines, is whether the data in the channel should start being read on the first edge, the first clock edge, or the second clock edge. Now, I remember I mentioned that the first clock edge and the second clock edge will be different depending on CPOL. Right? So if CPOL is 1, that means the first edge will be falling and the second edge will be rising. Whereas if CPOL is if CPOL is 0, the first edge will be rising and the second edge will be falling, right? But then together with CFA will then determine when you start reading data on the channel. Now you might say, well, isn't this a little pedantic? I mean, like, why does it matter that much? Well, this basically determines how the channel is synchronized and how you know when to drive data on the channel and when the other side is clocking data on the channel, right? So, like I said, if you're wrong about these settings, generally you won't be able to communicate, and it'll usually because all your bytes that you transact will usually be offset by 1 bit, essentially. Okay. So there's 2 different ways you could set CPOL and 2 different ways you can set CFA, and so that gives you 4 different kind of modes the channel can operate in. In addition to that, I mentioned earlier that when you read bits out of the channel, you can read them in either order from left to right or right to left. Most significant to least significant or the other way around. And that's a 3rd parameter that you have to define as well. You have to make sure that both sides of the channel agree on that as well. Okay, so let's look at some examples of this now. So part of this, one of the things that we want to convey in this course is how to read timing diagrams, and how to interpret, signal traces and see how that corresponds to these, transactions between devices. So this is a timing diagram, and the horizontal axis represents time, and then you've got your 4 signals here, and each one of these signals is shown as just a binary value that can be high or low, represented by the signal being high or low on its own vertical axis, right? So you can see that when things start out, the slave select is high, right? And the idea is that it's been high for it's probably been high for a while before before the events of the timing diagram begin to show what's going on. The clock starts out as low. So I can tell from looking at this that the CPOL is 0. The polarity of the clock is a 0. And then you can see that the slave select goes low for 8 clock cycles. It's not obvious there's 8 clock cycles. In fact, the only way you'd know that is if you'd have to count, you have to pick an edge. Pick an edge of the clock and count them. So if I pick the rising edge, I've got 1, 2, 3, 4, 5, 6, 7, 8. I've got 8 rising edges and 8 falling edges. That's the only way I'd know. You can't tell. I mean, I can't tell from. I mean, it's. I guess. Well, the other thing too is you notice we've got these dotted lines here that show each clock slot, bit slot, clock cycle. So you could also count those as well. But obviously, you'd only want to count the ones that are between the falling edge of the slave select and the rising edge of the slave select. Make sense? Okay, so you can see that the slave select goes down. That's when the channel is active. You can see the clock is going when the channel is active, and the clock starts out as 0. Now, what about the clock phase? How do we know what that is from the timing diagram? So the idea there is, notice that the clock seems to start a little later than the slave select. So the slave select drops, and then there's a half a clock cycle where there's a delay, right? That's what tells you that the phase is 0. If the phase had been 1, then the clock and the slave select would have changed at the same time. So being that it's 0, actually, wait a second, is that labeled wrong? So the idea is that the clock is going to indicate to the other side of the channel when it should be reading. So in this case, we can use the first edge, that's right, sorry, I got confused there first. This is the part, as I mentioned, this is always the part, it's a little hard to get your head around this. The clock, the first edge of the clock is when you're going to read the first bit. Okay. Now the reason you're doing it on the first edge there is you notice that the bits, the data lines, are already changed on that first edge of the clock. So what you don't want, what you're trying to avoid here is you don't want to clock the data in at the same time the data is changing. You want the data, the objective here is to have the data stable on the channel for as long as possible before you read it. And so because the bit changes a half a clock cycle before that first edge, that means that the data has had a half a clock cycle to stabilize, right, in the channel. And you say, what do you mean, why does it have to stabilize? Well, okay, so what we're fighting against here is it's a long wire. These are long wires. Long, meaning, not super long, but like this long, right? Potentially like, 3 feet long, right, is the idea. And those wires have capacitance. The longer the wire is, the more capacitance. So when I say stabilize, what I really mean is charge or discharge the capacitance of the wire is really what I'm talking about, right? So you want to, and also, the more time you give it to stabilize and charge up, the less likely it is that when you actually clock the data in that there'll be an error, right? Now you might say, well, wait a second, why half clock cycle then? Why not give it more than a half a clock cycle? Well, if you do that, then you start to intrude on the next bit's time, right? So if you read the data at an offset of a half clock cycle, which would be basically the opposite edge, in this case, if I'm reading on the rising edge, then I want to change the data when the clock is on the falling edge. This maximizes the time that the data has stabilized in the channel before I read it. So so C fa is 0, as indicated there, means that I want to read the data on the first edge of the clock. You might say, well, is it always the rising edge? Well, no, because it's the first edge of the clock is rising edge in this case because C pole was also 0. So because we have a combination of C pole being 0, meaning the clock starts out 0, and the fact that C fa is 0, meaning I want to read on the first edge, the first edge is the rising edge, right? Now if C pole were 1 and the clock started out high, then the first edge would have been the falling edge, and that's the edge I would have read on. You guys, does that make sense? Yes?
So when the SS signal drops, the data starts getting transmitted immediately, and then at the first edge it starts getting read? Is that what you're saying?
Yes.
Which is reading, the follower or the leader?
They're both.
Okay.
Yeah, because the MOSI is the slaves reading MOSI and the master's reading MISO. So remember they're both reading it because it's a bidirectional channel, and every bit is read. Every cycle you have a bit sent by both sides and read by both sides. So you want to. That's why it's really important that the slave knows what this timing is too, because it's going to have to start participating in this transaction right from the jump, right after slave select goes low. It's not going to have any time to, it's got to, this all has to happen in one transaction, one exchange, I should say. Okay, so in this case, C fa is 0, meaning read on the first edge, whatever the first edge of the clock may be, depending on C pole. Make sense? Okay. Now this is the slave select was low for 8 clock cycles, and as I mentioned, it could have also been low for another 8 cycles, but the number of cycles should be a multiple of 8 because it's a byte oriented. But the master was the part of it that decided that after 8 cycles were done. So this performed a 1 byte exchange. I sent a byte to the slave, and the slave sent a byte to the master, and done. Right? Now the problem with this, I'm going to foreshadow a little bit. I don't think. Yeah. Oh, actually, before I get to that, this shows all 4 combinations of C pole and C fa. So let's start over here on the left-hand side. So this is where we've got C pole 0 and C fa 0, and you can see that C pole is 0, meaning the clock starts out low, and C fa is 0 means that I'm going to read on the first edge of the clock. So what that implies is that the clock starts a half a clock cycle offset from the slave select, as I pointed out, right? When CFA is 0. Now, if C-pole were 1, CFA was 0, you still read on the first edge of the clock, except the only difference is now it's a falling edge, right? So the data, so the register or the flip-flop that's sampling the data on both sides of the connection have to be falling edge active, right? In this case, or rising edge over here. And the only difference between these two was C-pole. Now on the right-hand side, we've got CFA is 1, meaning that you're going to sample on the second. You're going to start on the second edge of the clock. And what that means in terms of the timing diagram is you'll notice that the clock is actually, it's still offset from the SS, but notice that the difference here actually is the MISO and MOSI are changing on the first edge, and so they're supposed to be red on the second edge, right? So I screwed that up earlier because I was pointing out that over here I was calling out slave selecting clock, but in reality you want to look at the clock and the data actually. So notice the data changes one cycle. The data is actually ahead of the clock over here, and over here the data and the clock both start out changing at the same time, right? So yeah, so ignore what I said earlier when I said look at the slave select in the clock. You want to look at the data in the clock. Make sense? Now it's hard to remember that though, because it's like, well, the easy way to remember it is that CFA 0 means that you're going to start earlier, right, reading the data. CFA 1 means you're going to delay reading the data. And so the difference is whether you're going to read the data on the first edge of the clock or the second edge. So that's CFA 0, CFA 1, right? Now, the way when you look at the timing diagram, one way you can see that kind of quickly is just looking at, when these three signals change, whether they all start out changing at the same time or if the data is preceding the first edge of the clock a little bit by half cycle. You guys with me? Make sense? Okay. Okay, so let's look at the actual data then. What's the data? What's the value being sent here? Well, you got to read the bits. The question is, when do you read them? Well, you look at, you basically, if CFA is 1, you find the second edge of the clock, whatever that edge may be, 0 or 1, depending on the polarity, right? And then you just read the corresponding values of MISO and MOSI below there, right? Now the way that this timing diagram is, it's got these dotted lines that denote each clock cycle, but in this case, the dotted lines just happen to fall on the read points, right, which is the second edge of the clock, right? Because of the way that, the CFA was set up. So basically all you have to do is you can use these dotted lines as your guide. So that's 0. So if you look at MOSI, which is master out, slave in, so this is the data going to the peripheral from the CPU, it's going to be 0, 1, 0, 0, 1, 0, 0, 0. Right? And then if I look at the data going the other way, it's going to be 1, 0, 1, 1, 0, 1, 0, 1. Okay? Now, the question is, what would I do with that? Well, if it's most significant bit first, then the way you read that would be from left to right in binary. So the first hex digit from master out, slave in would be 0, 1, 0, 0, which would be 4, right? And the second digit is 1, 0, 0, 0, which is 8. So 4, 8 in hex. Okay? So I just, in this case, I drew more dotted lines, but I drew these dotted lines when the value is changing, meaning the space between the dotted lines is the bit that you're sending, right? Whereas the timing diagram itself had dotted lines which just fell on the points at which you're reading the bits. Does that make sense? There's a lot of, the difference is whether you're looking at the read points, right? Which is where these little dotted lines, these black dotted lines would intersect the waves versus looking at each individual bit slot as an interval, right? So I'm showing these bit slots as intervals, but so yeah, in this case, MISO would be the MISO. This is the return data 1011010, which is 1011 is B and 0101 is 5 in hex. So B5, right? So the data that I send from the CPU is 48, and the data coming back is B5 in this exchange. Okay. Okay, and this is just another example. So in this case, this is different data. C pool 0, C fuzz 0. So this is a little different now. Notice everything's offset by a half cycle compared to the last timing diagram. So remember, in the last timing diagram, I had the dotted lines were the read points, but now you have to read between the dotted lines when you're reading these bits. So MOSI would be 1010. Notice that the dotted, my red dotted lines and the dotted lines that were originally in the waveform are now aligned with one another, and so the read points are in the middle. You guys with me? Now, why is that? Well, that's because on this one, C pool was 1 and CFO was 1. On this one, they're 0, both 0. So you can see the settings on the channel determine, this timing. If you're off with these settings, you can be a half of a cycle off. But more importantly, you're going to be more susceptible to errors because you're going to have one side, you're going to have a disagreement about when the data is being read. And so if you've got a disagreement there, you could have the one side of the channel deliberately trying to drive its data or change the state of the bits on the same edge of the clock that the other side is trying to read, right? Which doesn't give it that stabilization time, right? So you're going to be more prone to reading bad data if both sides don't have an agreement on what these settings are. You guys, does it make sense? Okay. Okay. So the problem though is, you might be thinking, okay, so now we've shown like you can exchange a byte, so what? Like how do you, if my goal was to send some data to a peripheral, how much can I do with just an exchange? I mean, ideally you have to be able to to send a value in along with some metadata, like tell it to do something. So like you want a programmed I/O style interface where you can give an address and a data, right? Right. And likewise, you want to be able to, so you might want to write a value to a specified address on the peripheral, or you may want to read. So in other words, generally speaking, you're going to be doing a programmed I/O style communication over SPI, where the peripheral is going to have these locations that you can read and write from and to, right? You guys with me? So we need something more than just these simple exchanges. So for that reason, whenever you use SPI, generally speaking, you're going to be doing some protocol on top of SPI. You're going to be building a transactional layer protocol on top of the exchange-based protocol that SPI fundamentally uses, right? So there's this terminology, and sometimes I screw this up. I'm going to try my best not to, but an exchange, when I say exchange, I mean that's what I just got done showing you, which is, you send a byte one direction and you get a byte back, right? So there's an exchange of one byte between both sides of the channel. Whereas a transaction is something where you do usually multiple exchanges in order to perform a more sophisticated transaction, right? Like a read or a write transaction. Okay, so that's a transaction. An exchange is that's just an exchange of one byte, whereas a transaction is I want to actually do something meaningful over the channel. So a transaction usually contains multiple exchanges, meaning that the master basically just holds that slave select down for more than 8 cycles. Some multiple of 8 cycles, but more than 8 cycles, right? Meaning more than one exchange is taking place. And then the first exchange usually establishes the master's requested operation. So in that first 8 bits that's sent, you have to squeeze in whether it's a read or a write operation, as well as, for example, if you want to do multiple words, multiple bytes in the data section, and the address. So in other words, what I'm trying to say is it starts to look like a network packet, sort of, where the first exchange is kind of the header of the packet, and then the subsequent exchanges are the payload of the packet, the data payload. You guys with me? So that's basically what's happening there. The problem is that there is nothing in the SPI spec that defines what the transaction protocol is. So the SPI spec just talks about MOSI, MISO, and basically how an exchange works. But when it comes to the transactions, that's up to the device that you bought that you want to talk to. And so that's application dependent, in other words. So in this class, we're going to be telling you what the exchange protocol is, and then having you, decode it essentially. So an example of that, as I mentioned, like if I want to read something, a value from the peripheral, I send 2 bytes, for example. The first, or the 2 exchanges, right? The first exchange is the address and flags. Flags meaning, this is the header, this is what I want to do. Now, as I mentioned, every time you do an exchange, there's always data coming in the opposite direction, whether you want to or not. So the other side is just going to send back zeros, right? So in other words, I'm going to send my header, and I'm going to get back zeros. You might say that's a waste. Well, yeah, but there's nothing for it to send, right, during that first exchange. Then in the second exchange, the second byte, if it's a read, then the master sends a dummy byte, and the slave is sending the response from the read, the data being read, back on the backwards channel. So again, even though I'm only really using half my bandwidth here, right? Because the first exchange, one of the sides was kind of dead, and on the second exchange, the other side was dead. But unfortunately, that's just the way that people build these protocols on top of SPI. And then likewise, if I'm writing, then both bytes will just be one direction. Like the master will send an address and its intention to write, and the first byte and the second byte is the data it wants to write. There's nothing to come back, right, necessarily. You may just get zeros coming back, right? You guys with me? So you might be thinking, well, this kind of seems like kind of a hacky way to handle this, right? I mean, you've got this capability of SPI of doing exchanges. You never really do a true exchange. It's always just one side or the other is sending meaningful data, and the other side just sending back zeros, right? So why do the exchange? Why always do exchanges? I don't know. That's just something that you have to do for SPI. Now there are other protocols, however, like I think there's an audio protocol that takes more advantage of the bidirectional nature. But when you're doing reads or writes, you just have to deal with the fact that you're kind of hacking, the physical layer of the protocol is having to be sort of bastardized in order to perform this programmed I/O style read and write behavior. Okay, so here's an example of what I mean. So let's say I want to do a read. So the master wants to read a register on the peripheral. So basically, you'll notice notice this says CS instead of SS. This picture I got out of a data sheet for one of the devices that we used to use in this class. I think this is from the accelerometer. And so sometimes when you read device data sheets, they'll give slightly different names to these signals. In this case, they use CS, but it's the same as SS, so don't worry about that. But you'll notice that the CS is low for 2 exchanges or 16 cycles, 16 slots, right? 16 clock cycles. You'll also notice that the way this is shown, and this is kind of obnoxious actually, but the clock is not a square wave. It sort of has this angled thing. It shows that it kind of goes off at an angle, which is the reason they do that is because that's actually a more accurate. This is actually looks closer to what a clock signal looks like, because you think of a clock as a binary, but it's really an analog signal. And when you drive the clock up and drive it down, it sort of rolls up and rolls down. It looks kind of like a sine wave, because you have to charge up capacitor and discharge a capacitor. And so a lot of times you'll see this like more of a gentle up and down on these timing diagrams. But to me, this just makes it harder to read. I don't like this style. But anyway, so you see there's 2 exchanges, and in the first exchange, I've got 8 total bits. We can't change that. The first bit is a flag that says whether I'm reading or writing. The second bit is the multiple or single, a flag that says whether I'm going to do a single byte transaction or a multiple byte transaction. And then the next 6 bits are the address. In this case, are numbered from 5 to 0. So most significant to least significant, so left to right. And then in the second exchange is, if this were, assuming that this were a read, then I would have data coming back. The data, my requested data, as indicated by the address bits, would be coming back. Whereas if this were a write, I would be sending the data I want to write in the second exchange, right? It's 2 exchanges, 1 transaction. So this is one read, or it's not obvious if this is read or write, but it's either a read or a write. It's just generically shown here. It's a read or a write transaction, but it's comprised of 2 exchanges, right? Okay, that's what I just said. Okay, so here's a write. So if you do a write, and again, this came from that data sheet again. So in this case, they don't show the MISO. They only show the data going from the master to slave, and they call it SDI, serial data in, I guess. I actually don't know what that, but that's obviously meant to represent MOSI, right? Master in, slave out. Or sorry, master out, slave in, MOSI, right? That's your data going out, right? And this is a write. So in both exchanges, you've got bits going out, no bits coming back, so they don't show the incoming signal, whatever they're going to call that, right? Also, this one's called SPC, which is, again, stands for serial peripheral clock or something, but it's just the clock, okay? And then so that's the write. Okay, so let's look at an example of one of my examples. So this timing diagram, I just want to get you used to the idea that there's different data sheets will have different styles for these timing diagrams, but all the ones that I have in the quizzes and the exams for this class, I generated. This is from I generated this from a LaTeX package that generates waveforms. I really like this one. I think it's clear. So most of the styles you'll see look like this. So I put the CPOL and the CFA and whether it's most significant bit or least significant bit first on here, right on the top. And like I said, the SPI doesn't define what the bit ordering is that you send across. Now, I2C and UART do. So some protocols do specify the bit ordering. SPI doesn't. So we have to list that here, right? And usually if you're using like an Arduino or like a Raspberry Pi, something that has an SPI endpoint on it, interface, SPI channel, that's something you program ahead of time. Well, you or the driver, the device driver, right? Programs that in the hardware, sets up the hardware for these settings. And of course, you would have to tell it ultimately what those settings are from the data sheet of the device you're trying to talk to. Now you might be saying, wait a second, hold on. What if you want to put multiple slaves on one SPI channel, but they have different settings for CPA and CFOL? Well, then I don't think you can. If you're going to do that, they all have to agree. right? But like I said, usually you don't do that anyway. It's not, in my experience anyway, it's not very common to do multiple slaves. Usually there's just one, there's just two sides. Okay, so with SPI, I squared C is, the other protocol we're going to talk about is a different story. Okay, so here's an example. So in the following SPI transaction, assume the transaction address is stored in the least significant 5 bits, and the read-write flag is stored in the most significant bit of the first byte transmitted from the master to slave. So in this case, you've got 1 bit for read-write, and you've got 5 bits for the address. Oh, wait a second, that's 5 plus 1, that's 6. That's only 6 bits. There's 8 bits. What about the other 2? You ignore them. Right. Also, notice that I put a little bar here over the read. That means that's indicating that the read. If that bit is 0, you're reading, and if it's a 1, you're writing, because that bar is meant to represent a logical complement. Make sense? Meaning the read is active low, write is active high. Right. Okay. So how do I know what's going on? Well, the first thing you got to do, yes?
It's a write transaction. You can tell because MISO is inactive the entire time.
Yes, yeah, that's a good point. Yeah, so MISO is flat. That's a good point. That probably means unless you're reading and the data coming back is all zeros, it means that this is probably a write, just based on the fact that this thing is flatlined the whole time. So probably you're doing a write operation. But just to be sure, all you have to do is look at the first bit. Now, CFA is 0, so I'm sorry, CFA is not 0, CFA is 1, which means I got to look at the second edge. Sorry, second edge is here, right? Yeah. First edge, second edge, right? Second edge, which again, it falls on these dotted lines. So in this case, the read points are on these dotted lines. And you can see that MOSI is a 1, right? And 1 means write. So it's a write based on the actual bit in that first bit position. So what I've done here is annotated this guy. I put my dotted lines to denote the beginning and end of each bit slot. So my dotted lines are indicating when the data bits are changing. So when you read the values, you're reading between these 2 dotted lines, whereas on this timing diagram, they have additional dotted lines that show the read points, right? That just, the way it's set up, again, the dotted lines on the waveform are just a guide to show you how wide a clock cycle is, but that doesn't necessarily mean, you don't really know how that lines up with when you're supposed to be reading the data until you look at the settings on the channel, right? So, so then I show basically just MOSI, MISO, and just, note what those bits are. So that's, unfortunately, that's really the only way to do it. You have to just kind of work through and mark what these guys are. Now you might say, well, wait a second, why not just show the bits there on the timing diagram? Why have a timing diagram where you have to interpret, a graph, to determine whether it's 0 or 1? Well, it's meant to look like a logic analyzer or an oscilloscope, right? This is meant to actually, indicate a voltage up or down, right? So that's why you have to interpret these lines as being high or low, and you're just translating. So in this case, that's a 1 1 0 0 1 0 0 0 1 0 1 1 0 1 0 1, and so those are marked on there. And then the other problem with this is that it's kind of hard to tell, even once you do that, where the first exchange ends and then this next exchange begins. So you've got to count. You got to count off 8 bits, and then once you do that, you can start looking at, well, that's my read-write bit, and then I mentioned it's 5 bits, 1, 2, 3, 4, 5. Those 5 bits, the least order 5 bits, sorry, the low order 5 bits in the first exchange is the address. So the address I am writing to, and I know I'm writing because that first bit is 1, is 8. So the master's saying, write a value to address 8, and in the next exchange, I'll tell you what that value is. So you got to go to the next exchange and you see what the value is, which is 1011 is going to be B, B in hex or 11 in decimal in the first nibble. The second nibble is 5, right? Second. So in hex, it's B5. So write the value B5 into address 8, right? That's what this is. And all this stuff from the slave to master is just all zeros. Now, if there were bits in there, I think they would just, it depends on the hardware setup that you're using, but generally I think they just to be ignored, right? Okay, yeah, and I've got everything labeled there. Read-write bit, DC stands for don't care, address, this whole 8 bits are don't cares, these whole 8 bits are don't cares, and then this is the data up here. Okay? So yeah, master writes B5 into address 8. Okay, so here's another example. Same idea. But in this case, I don't show, I just show the, the arrows pointing to the MOSI in the first exchange and then the MISO in the second exchange, because this one is a read operation as indicated by the first bit being 0. So I am reading, the request from the master side is to read address like 0, first hex digit 0, and then 1011, which is going to be again B. And then in the second exchange, because it's a read and not a write, now this wire is dead, it's all zeros, and the wire coming back is the hex value E3. Okay, so that's the read. Okay, make sense? Okay, and then, so also, there's this capability for doing multiple reads and multiple writes. So instead of only doing one read or one write at a time per transaction, you could go into like streaming mode, essentially, where in the first byte in the header, you can say, I want to do a read or write, but I also want to do multiple words, multiple bytes, and in that case, the transaction is more than 16 cycles. It can be more than 16 cycles, right? So in that case, this protocol, and again, this one came from our accelerometer data sheet, but you can see that the read-write flag comes first, and then the MS bar, meaning multiple or single, flag comes next. So if that bit is 1, it's multiple. If that bit is 0, it's single. And then you've got your 6 bits of address in this case. And so if you're doing a multiple read or write, the address is the initial address, and then subsequent words would assume that there's an increment happening on that address, right? So if I want to write 10 bytes, the first address would be that address, and the next 9 would be an incremented form of that address. You guys with me? Because you only send one address. You don't send an address for, if you do a streaming operation, you only send the initial address, and then you assume that that address is incremented. So that way you're reading or writing a consecutive chunk of addresses. Okay? All right, so let's, so there's one transaction. In this case, there's 3 exchanges, so it's 3 times 8, 24 cycles. Okay, so here's an example of that. So we've got a multiple, in this case, multiple read. So notice that I've got the first exchanges, I have it labeled as header, and then read data 1, read data 2 is the next 2 exchanges. The header has a read bit is 0, means I'm doing a read. Write, actually. A write. No, that should be a read. No, actually, it's a read because we got data coming back. So that must be that's actually a bug, huh? Read, write. Oh, no, it's right. No, it's a read. Yeah, so I guess that should be, if it should have been, I think that bar is in the wrong spot. Yeah, there we go. Yeah, there we go. Is that what I had before? No, that's not. Okay, well, okay. So, yeah, so actually, this is a read because the first bit is 0, but the reason I know it was a read was because you see this data coming back, right, to the requester on the MISO, the feedback line. So it must have been a read, which meant that the read bit indicator should have been a 0. So you put the bar above the R. Makes sense? Okay, so and then the multiple is the logic high. So there's a 1 there for the next bit, which means I'm going to do a multiple byte transaction, and then the address is 001110, which is just going to be a E, 0E in hex, and then this in the second and the third exchanges, the peripheral knows what address is being read, and so it will send a sequence of bytes starting at address 0E for as long as I keep the SS signal down. Everyone with me? Okay, so that's a streaming read. And then there's a write. So here's an example of a write. Yeah, so I had that one wrong there too. Okay. Sorry, just noticed that. So again, this is a write, which means that the first bit is a 1, which means write. And I know it's a write because there's no data coming back. It's just all being sent by the CPU. Yes, your question?
Just stretch it.
Oh. All right. Okay, so I'm going to talk really quick about having multiple slaves. So there's 2 ways to do that. You can basically have. So the problem here, yes.
Going back to the prior slide, the multiple / single. How does it know when to stop? Is it default to 2, or is there some way of indicating end streaming?
The streaming, the indication is done with the slave select. So in the slave select, so the master. So basically, what that means is that if your peripheral supports streaming, then the master controls how many words are sent or how many bytes are being read or written, and there might be a limit. Maybe the data sheet will say, well, you can only do that up to 6 or something, but it would be application dependent, right? But in the protocol, the idea in the protocol is that as long as you hold that SS line low, it'll continue to do the read or write, right? On consecutive addresses. So you give it a starting address. If you start out at address 10, then the third word in the transaction or the second word in the data segment will be 11, and then 12, and then 13. So there's there would be a counter on both sides of the connection that would count starting from that initial address. Make sense? Okay, so if you have multiple, if you want to have one CPU and multiple peripherals on an SPI, you can do that. The problem is that you're limited to those four wires, right? And the 4 wires are identified. They're actually named according to assuming there's 2 sides. So one way to do it is to have the master actually have one slave select for each slave, and the slaves just have the 4-wire connection. And then the MOSI and the MISO are going to be fanned out, right? So the MOSI is connected to the MOSI on all the slaves, and the MISO of all the slaves are all fanned in to the MISO, right? Now that is dangerous though, because that opens the potential for those slaves to double drive. Like if this slave is this guy is trying to send a 0, and this guy's trying to send a 1. They're fighting each other, right? So the presumption here is that these MISOs have to be gated connections where they could be, disconnected on each slave. The slaves have to disengage from that MISO when they're not sending data, when they're not active, when they're not part of a transaction. Another approach is you can use a daisy train approach where you can treat this whole thing like a big shift register where the MOSI comes out of the master and goes in the slave, and then the slave is the master for the next slave, and that slave is the master of the next slave. So you create this shift register. The problem with that is that all of the slaves have to be involved with every exchange, and the exchanges have to now have a number of clock cycles that would allow all the bits that form this like sort of 8 times 4 bit register to shift all the way around, right? So in this case, it would take, 24 bit times, 24 cycles to move data, say from this master down to this, the last slave on the daisy chain. But you could do either approach, but like I said, generally with SPI, they're usually just 2. Okay, or 2 endpoints. Okay, so now I want to talk about lab 1, and I mentioned I'll go through this in detail in the labs on Wednesday and Thursday. But I just wanted to give you, while I have everyone here, I wanted to introduce this. So the objective here is to read we're going to give you a trace file that essentially just contains a waveform like this, right? So here we're showing, we're giving you a waveform that's graphical. Like I said, I rendered this in LaTeX using a package called TEEX. And so we'll ask you to decode this visually on the quizzes and the exams, but in lab 1, we're going to have you read this out of a text file, which we call a signal trace file. But we give you an API that's going to help you, interpret that trace file. But the objective is to read the trace file and then interpret it, decode it. So take the trace file and basically convert it into a little command that says read or write, and then the address, and then the data. Make sense? So you're just going to decode. Now, there's 3 parts to the lab, and they build on top of one another. So, if you finish all 3 parts, then the code that you wrote for part 3 will actually, work to fulfill the requirements of the previous 2 parts, right? So you don't have to write 3 separate programs. You're just writing one program with an increasing number of capabilities. In the first part, you're just going to be able to decode simple read and write transactions for CPOL 0 and CIFA 0. Part 2 is the decode to allow streaming transactions. And then part 3 is to allow different CPOL and CIFA values. Does that make sense? So as I mentioned, we wrote a parser for you, and we provide you with an API that's for C and Python. So you can use either language. If you want to use a different language, then you'll have to write your own parser, which frankly is not too difficult, because the text file is pretty sensible to read. And then we also give you this grading script, where if you want to test your code and you want to find out essentially what grade you're going to get on it, you just run this script, and it'll take your code through some test cases. Now we're going to use different test cases though when we grade. We're going to give you test cases for testing your code. We're going to use different test cases when we grade it. But there's really only, there's sort of, generally speaking, if you pass all the test cases we give you, hopefully it'll work for the test case we use to grade it. Yes?
Yeah, usually when we're grading, if I remember correctly how we did it last time, we have basically just a superset of the data that we give you all for testing. So if you pass all your test cases, you should have encountered all of the different ways that we could feed data in. And so when we feed in entirely new test cases that have the same waveform patterns in them, yeah, your code should still work.
Okay, so the signal trace, basically the idea is that it's a waveform like this. Now this is this one is not an SPI waveform, obviously. This is just a general waveform. But what I wanted to note on here was that the signal trace is set up to be basically observations at specific points in time. And then those observations are just listed on a line of text. So in this case, we've got this signal trace, and we have these observations at different points of time. Now notice that they're all at 0.001, basically 1 millisecond. Well, I've listed them all at 1 millisecond, but notice some of them like are black and they don't have a vertical line, which means these ones were skipped in the file. So the file is, these observation points are not necessarily all going to be uniform, right? Okay, so that trace translates to this in the signal trace, and you can see that's basically just a table. The first column is the time when the observation was made, and then the subsequent columns are each of the signal values, 0 or 1. And then the first line is the number of observations, the number of samples, and the second line is the headers, so the signal names basically. So, clock, S1, S2, S3, those are the signal names. And then you have your observations. The only thing that's weird about this format is that notice that there's no header for time, right? So the headers are just the signal names. So what you end up with is, you'll notice, you see how it looks like there's an extra column here. And that's because, the second row is the width, the bit width too. Sorry, I forgot to mention that. So the first line are the names of the signals. The second line is the bit width of each signal, which in this case are all ones. And then starting from the fourth line actually, because the first line is the number of samples, signal names, number of bits for each signal. Then starting with the fourth line, right, the fourth row, that's just a tabular format. But the first column is the time, right? So if you look at this like a table, it looks a little strange because there's the number of columns is actually one greater in the bulk, the main part of the data than it is in the headers, because in the header there's no time header. Does it make sense? Right, so that's why it looks like there's an extra column. I know I didn't explain that very well, but so basically this clock is that's the clock, and that's S0, and that's S1, and that's S2. But the good news is you don't really have to worry about that. I'm just mentioning this so you understand what's going on. So basically sample, signal width values. You don't really have to know that because we provide you with an API. And like I said, in C and Python, this shows how you initialize it. And then we just give you a function call that says next edge and signal at. So you call signal at to get the signal at a certain time, and the next edge will find the time in which you have the next clock edge. Makes sense? So there's basically three functions that you have to use. Their initial one to set it up, and then next edge and signal at. Make sense? Sorry, I'm a little bit over, but I wanted to get through that. I'll go into a little bit more detail on this during lab, so you guys will have enough to get started on. If you're interested in the lab sheet now, it's posted. And if you want to check out the skeleton, which has this, all the test cases and the scripts and the API and the skeleton and the templates, you can download that off Dropbox. Okay? Okay, thank you.